Greetings, hello, welcome. Let's learn about double interpolation. Yes, this time, double interpolation it is. Okay? So hopefully you've went through the first video and we'll cut right to the chase in this one. Double interpolation. So we have this TS diagram drawn. Speaking about this one, yes. Okay. You can start at any state you are comfortable with to find the properties. Normally, the properties we are interested in this case, seeing that we have flow, we are speaking about the total energy of the system, and that is enthalpy. We are interested in H, and we're also interested in this is enthalpy. H is enthalpy. We're also interested in S, entropy. Just, the process can be isentropic and all that. And we're also interested in V at some of the states. Okay. So you can start at any state that you feel comfortable with. But I'm going to start at state H. Then I'll move on to state 9. Probably also state 10. Because those states require, well, that's where I've seen that there's double interpolation needed. Okay, so it's state 8. The pressure is 10 megapascal, temperature is 600 degrees Celsius. Alright. State 8. What do I know? 10 megapascal is my pressure, and I also know that my temperature at state 8 is 600 degrees Celsius. Alright, cool. So the first thing that I need to do is just check my properties on my steam table. Now, if I did not know that this was steam, then I would go to my saturated liquid table and do the checking. But reading the problem statement, I am told that steam is entering a turbine at 10 megapascal and temperature 600 degrees Celsius. So this right away is steam, and water at 600 degrees Celsius is, well, it's no longer water, it's vaporized. Okay, cool. So let's just go ahead to steam table. What table is, I don't know the steam table, so should be table A6, yes, yeah. So table A6, we are looking at table A6. Table A6, we go at 10 megapascal. This is 10 megapascal, and it's 600 degrees Celsius. So takes us all the way. Alright. So I'm looking at the regions of 3625. 3625, that's my enthalpy. Alright. H8 is 3625.8 kilojoules per kilogram, and my S8 was, what was S8? S8 was 6.9045. 6.9045 kilojoules per kilogram Kelvin. Alright, that's done. Cool, state 8 is done. Okay, now we move to state 9. State 9 is at the pressure of 1.3 megapascal. 1.3 megapascal, and temperature 9 we don't know. However, what we do know is that S9 is equal to S8 is also equal to S10. And you ask, how do we know that? Well, we know that because the TS diagram tells us. The TS diagram tells us, looking just at the TS diagram, if you extend this vertical line all the way down, you'll find out that S at state 11 is equal to S at 10, is also equal to S at 9, is also equals to entropy at 8. So if I have entropy at 8, I have all these entropies. Do you see that? Isentropic. Cool. Well, yeah, cool. Yes, so this is the same as S11, which 6.9045 kilojoules kilogram Kelvin. So by the end of this video, you will be able to double interpolate. Trust me. Alright. So let's go. So yes, in order to fix a state, you need two properties, and we have those two properties. We have the pressure at state 9, and we have the entropy at state 9. Entropy is a property, pressure is a property. Therefore, our state can be fixed. In other words, our state is defined. So let's go ahead and read H9, because S9 we already have. We know that this, okay. Let's say maybe you had a doubt that what is this steam or is this not steam? What you would do is go to your saturated liquid table, and at the pressure of 1.3, at the pressure of 1.3, we do not have a pressure of 1.3. This is not a saturated liquid table. Okay, maybe I can pull up a saturated liquid table. Okay. All right. So at the pressure, let's go to table A6, A5 I mean. All right. At the pressure of 1.3, that is 1,300. Yes, here we are. At 1,300, Okay, let's do this. Okay, so our pressure is 1.3 megapascal at step 9, and our entropy is 6.9045 kilojoules per kilogram Kelvin. Let's say I did not know that this was steam. So what then I will do is that I'll go at the saturated liquid table at my pressure of 1.3 megapascal and go and compare the value of my entropy, at SF, of course this is the minimum is SF, and the highest is SG at this pressure, and see if my entropy value falls in that range. Okay, so if my entropy value, if S9 falls in that range between SF and SG, then that tells me that the property, or I can read off my properties. I will need to find quality, in other words, if it's in between. However, if S9 is on the other side, that simply means if S9 is greater than SG, than the saturated vapor, if this was my dome, my saturation dome, SG will be here, SG. So if S9 was somewhere here, that would simply mean it's superheated. If it was less than SF, then that means it will be a compressed liquid. However, if it was greater than SF but less than SG, that means I'll be in this region and therefore I'll need quality. Hopefully that makes sense. Okay, so just to show, this is how you do it. You go to a saturated liquid table. This is table A5 at 1.3 megapascal, which is 1.3 kPa, and then I'll compare my enthalpy values. This is SF and that is SG. So looking at SF, it's 2.2, it's less than that. So looking at SG, it's greater. What am I saying? Looking at SG, it's less than the entropy value we have. Therefore, guess it? Yes, you guessed it. We are looking at a superheated state. So our values should be collected from the superheated region. Yes, so superheated region at 1.3 and at the given entropy, that's exactly where we are going. So superheated region, superheated tables at a pressure of 1.3, which should fall somewhere. It's supposed to be somewhere. Yeah, 1.3 is supposed to be here. I have 1.2, I have 1.4, but no 1.3. What do we do? Exactly. That's why this video is made, to know how to deal with such a case as this. So don't worry. We We're here to double interpolate. Let's double interpolate. All right. So this is what I normally do. First, what I normally do is I'll delete that. I normally do not delete that, but it has to go now. Yeah, it's gonna take long. Okay. One more. Yep. Don't know where to paste it, but it's not needed. So, this is what I normally do. I'll draw a table. Okay, so I have 1 point. I have 1.2 and 1.4. So I'll draw that 1.2 and 1.4 that I have. And I'm looking for 1.3. Okay, so what else do I have? I have entropy. I'm looking for 1.3 at the given entropy of 6.9045. The given entropy of 6.9045. So I can run this across to the other pressures, the other pressure regions. Yes, double interpolation has commenced right now. Okay, so I can run this across okay, I run this across. So I'm looking I'll go to the region of 1.4 megapascal at 6.9045, and I will read off my enthalpy value that corresponds with 6.9045, if it's there, of course. If it's not there, then I'll have to interpolate. I'll do the same at 1.2 megapascal. 6.9045. Okay, at my given entropy value, I'll go and read off that which I require. It can be temperature, it can be volume, but in this case what we have is entropy, so we'll use entropy. After using entropy, then we'll use pressure. You will see what I mean. All right. Okay, cool. So let's go at the pressure of 1.2 megapascal at this entropy, at the given value of entropy of 6.9045, and read off our enthalpy. Okay, 6.9045. So there's a problem here. 6.9 is in that region. So enthalpy is somewhere in there. That tells me I need to interpolate. Do you see that? 1.2, 6.8313 and 7. So I need to interpolate between those regions. So I need to interpolate between these two and those two to get my enthalpy at 1.2 megapascal. Okay, so let's go ahead and do that. We'll interpolate between 6.8313 and 7.0335. 7.0335, and between 2935, 2935.6, 3046.3, 3046.3. So we need to interpolate, get the value there. I'll call it HA, and we'll call this one HB. So HA and HB we need to find. How do we get HB? Well, we need to go rid of HB at that given entropy value. So we go at 1.4, pressure of 1.4, and we see where 6.9045 falls. 6.9045, 6.95. So it's in between here, between those two values. So it's in between 6.7488 and 6.9553. 6.9553, and we'll interpolate between those given enthalpy values of 2927.9 and 3040. 3040.9. Okay. So that's the first stage. So double interpolation. We interpolate at the pressure of 1.2 megapascal. Then we interpolate at the pressure of 1.4 megapascal. We get those values. Then we interpolate at 1.3 megapascal. All right. Check this out. Let's go. All right. So to interpolate, this is manual interpolation, of course. To interpolate, you would say, all right, you would say 6.9 is what I'm looking for. So it's a 6.9045 minus the lower limit, 6.8313, divided by a higher limit, 7.0335 minus 6.8313, which is my lower limit. I'm looking for an enthalpy value that correlates with my given entropy, so which is HA. So HA minus the lower limit, 2935.6, divided by enthalpy, upper limit enthalpy, minus lower limit enthalpy From here, just make HA subject of the formula. This will be equal to 6.9045 should be minus 8313 divided by 7.0, 6.8313. All of these multiplied by 3046.3 minus 29356 plus 29356, and this will give me HA and HA value. Oh, right, if you work that one out, you get an HA value of 299,254 kilojoules per kilogram. Confirm that on your side, please. But yeah, that's what you will get. And then we'll do the same for HB. We would say, okay, entropy we are looking for is 6.9045. We'll subtract the lower limit, 6.7488, divided by higher limit, 553, minus 6.7488. All of this must be equivalent to the enthalpy that I'm looking for at the given entropy minus the enthalpy that correlates with the lower limit, 2927.9 divided by 340.9 minus 2927.9, and you work this out, it will come down to the same thing as 6.9045 minus 6.7488 divided by 6.9553 minus 6.7488 multiplied by 3040.9 minus 2927.9 plus 2927.9. And all that will give us an enthalpy value of 3013.10 kilojoules per kilogram. Okay, so this is our enthalpy at our HB, enthalpy at at 1.4 megapascal. Yes. And this one is our enthalpy at 1.2 megapascal. But we're not interested in any of this. We're interested in enthalpy at 1.3 megapascal. So let's just indicate in our table what we know. Okay, we know enthalpy, we know that value now, which is 299.2.54, and we know this value now, which is 3013.10. Now what we need to do is find out what is our enthalpy at step 9. Then we're done. To do that, we'll now use the pressure to interpolate between the two pressures and our new values. So let's do that. So to interpolate between the two pressure, the pressure of interest is, we have 1 point, okay, pressure of interest is 1.3 minus the lower limit pressure, which is 1.2, divided by the higher limit pressure, 1.4 minus 1.2. All of this must be equal to what we are looking for, H9, that corresponds with 1.3 megapascal minus the pressure that corresponds, the enthalpy that corresponds with 1.2, which is 2971.99 divided by 3013.10 minus 2971.99, and this will give us H9, which is equals to 1.3 minus 1.2 divided by 1.4 minus 1.2, 013.10 minus 2971.99 plus 2971.99, and this will give us an enthalpy value of 2.54 kilojoules per kilogram. So yeah, that's how you do double interpolation. So basically you interpolate between the two tables given, using your given entropy value. In this case, the parameter that you are given, it could be entropy, temperature, but in this case we had entropy, so we used entropy to interpolate, find out what is the value of enthalpy at our given entropy, and once we found those values, then it was easy to interpolate between the given two pressures, given that our known pressure was 1.3, which we were interested in, and then we were able to find our H9 entropy of 299.2.54. So enthalpy at state H9 is 299.2.54 kilojoules per kilogram. So that's how you do double interpolation. Continue learning. God bless you and keep safe.